Good morning. No, good afternoon. Yeah, good morning. Hope you're doing well. So today in class we'll talk about gravitational field strength and do a couple of example problems on that. Then we'll also talk about inertial and gravitational mass. So gravitational field strength. Imagine you have a body. Could be a body in space or uh, even you yourself, any mass, anybody that has mass, has a force of gravity acting downwards on it as mg. Now that force of gravity acts through the center of that object. That force of gravity acts through the center. So let me just try to represent it here, through the center. Now the idea of a gravitational field strength, just like you can have a magnet will attract things that are near it. If this is the South Pole and that's the North Pole, then the magnet is going to have a field around it, right? It's going to have a field around it. It's called the magnetic field, and in that field, objects will be attracted to the magnet. If an object is brought closer to the North Pole, then it's going to get that charge on the North Pole. If it's going to closer to the South Pole, then it's going to be attracted to the South Pole, and it will get electromagnetism from the South Pole. So not electromagnetism, sorry, it will just be attracted, and it will have it will be attracted to the South Pole. So the idea is that any mass, or all masses, also attract objects towards it. We see this with Earth. If a meteor goes so close to Earth, actually meteors get close to Earth, and as they're flying close to Earth, their paths are warped to go around the Earth. They don't collide into the Earth, but they bend around the Earth. Satellites that also go around the Earth end up orbiting the Earth because Earth has gravity. You've heard of things like gravity assists, where you have the current, I don't know if it is Voyager, something, has been able to travel farther with less fuel because it keeps on getting gravity assists from planets. So basically, planets slingshot it with kind of a gravity assist to go to different places. Now, this tells us that planets or masses have fields, gravitational fields, and scientists don't know exactly what is in those fields, like what those fields are made up of, whether it is light or whether it is photons. But what is observable is that there's a field that attracts all objects towards masses, smaller objects towards bigger masses. Now here, that's what we call the gravitational field, and here on Earth, we experience that in the form of acceleration due to gravity. The Earth pulls on us with an acceleration of 9.8 meters per second. It pulls on anything that's within either on the surface, above the surface, or within a couple of kilometers above the surface, with an acceleration of 9.8 meters per second. Now this is what is called a gravitational field strength of a mass, right? This is the one for the Earth, but for a mass, it's basically the force exerted per the unit force exerted per kilogram mass of an object. I hope that makes sense. I'm getting this from the idea that F equals ma. So if F is equal to ma, then A is equal to F out of m. So the gravitational field strength, this acceleration due to gravity, is the force that's exerted, because that's newtons, per kilogram mass of an object that is in its gravitational field, or that is above its surface. Now, we're building on this idea of F is equal to ma. We saw yesterday in class that if you have two masses, you have m1 and another small mass, m2, then they are attracted to each other by a gravitational force from Newton's law of gravitation, that is G, m1, m2 out of r squared, or some books use b squared out of b squared. So I'll just use r squared. But we also know that because this mass is accelerating towards that mass, because it is pulled in by gravity, then Newton's second law, F is equal to ma, also applies. So F is equal to ma, and this m is m2a, and Fg is equal to gm1 m2 of r squared, are both forces acting on this object. This is also the force due to gravity. So what we know here is that these forces are equal. These forces are equal and opposite, because this is pulling on that, and that is also pulling on that. Since those forces are equal and opposite, I'm going to equate them. I shouldn't have called this force Fg. This is force due to inertia. This is an inertial force. This is a gravitational force. So the inertial force is equal to the gravitational force. The gravitational force is G m1 m2 out of r squared. The inertial force is just m2 times acceleration. I hope you can see that m2 will cancel out. Because if I have m2 on this side and m2 on this side, it cancels out. And what I'm left with is just, oops, straight line. What I'm left with is just A is equal to G m1. m1 is now the mass of that big planet divided by r squared, and r squared is going to be the radius of that planet. So to make this better, let me draw this planet such that it's so big and this small mass is within the surface of, like it's above the surface, but it's within the radius of that bigger planet, right? Or if I was using d squared, then it would be more believable, because I just want to avoid the confusion of this being r, yet the distance here that I've drawn between the particles is obviously large. So just imagine an object that's above the surface of the Earth. This would be true. If that object is some kilometers away from the surface of the Earth, then you'd add the radius to the distance apart. So yeah, in calculations, if it was in the surface of the Earth, you would use the radius of the Earth. If it was on the surface, if it was outside, then you would add this radius plus that distance from the Earth to that object, if it is known. So this formula here is very important because it is true for any planet. Any planet will pull an object towards it with an acceleration that's equal to g times the mass of that planet divided by r squared. Now, something interesting here that I did and probably did not mention was that I equated the force of gravity to the force of inertia, the force due to inertia. The force due to inertia, remember, is if I'm thinking of objects back here on Earth, if you just think of an object on a table, the inertial force that you apply to it to move it horizontally is equal to the mass of the object times the acceleration of the object. At the same time, the force due to gravity of this object, if this acceleration is 9.8, then the force due to gravity of this object is also going to equal to mass times gravity, right? Mass times gravity. Now, these forces are equal. If these forces are equal, this is the inertial mass, this is the gravitational mass. If these forces are equal, that means mi times a is equal to mg times g, technically, which g is also a. So the a cancels out, and I'm left with mass inertial is equal to gravitational mass. This is an interesting idea or interesting observation in physics, because experiments show that these masses are the same. The gravitational mass of an object is equal to the inertial mass of an object. The force with which Earth's gravity pulls down an object, the acceleration that it gives it, is the same force you get if you give that object a linear acceleration of 9.8 meters per second. Now, and I hope that makes sense. I hope that makes sense that if you give an object a linear acceleration of 9.8 meters per second, the force you calculate from this is going to be equal to the force of gravity pulling the object downwards. That turns out to be true, and scientists still have not yet explained why those masses are the same, why those masses are equal. This problem has been around for a couple of years, and hopefully you'll be the first one to solve it. But anyways, so inertial mass, gravitational mass are equal. That is true. The gravitational field strength of any mass is g times the mass of that object divided by the distance. This is going to be the distance that any other object that's within its field is from that mass. Let's look at an example. Find the acceleration due to gravity at the Earth's acceleration due to Earth's gravity at the distance of the moon. So you have the Earth, right? You have the moon somewhere here. So already I have radius of Earth in here, and then I have this distance from the Earth to the Moon, right? And then I have the radius of the Moon, So if I'm calculating the acceleration due to gravity, or due to the Earth's surface at the distance of the Moon, it's basically asking you, what acceleration are you going to feel from the Earth when you are at the Moon? That's what it's asking you. So that's going to be G times mass 1, which is the mass of the Earth, or the mass of that planet, divided by r squared. I'm going to use d squared because that d stands for the distance from the center of the Earth to the center of the Moon. Now, fortunately for us, that distance is known. I did not include it in this slide, but that distance is known. Let me just do a quick Google search. Distance from Earth to Moon, yeah. So we know G is 6.67 times 10 to the minus 11. We know mass of the Earth is 5.98 times 10 to the 24. And the distance from the Earth to the Moon is 3.84 times 10 to the power 5 squared. So if I plug all of this information into my calculator, 2.84 times 10 to the power 5. Yeah, if I plug this into my calculator, I end up with, let's see. No, actually, you can plug that into your calculator and see if you get this answer. If you don't, send me an email or something. Alright, moving on. Planet Krypton has 4 times the radius and 2 times the mass of the Earth. What is the best estimate for the magnitude of the gravitational field at the surface of planet Krypton? Now I know that I can start with what I know. The G at the Earth is G, mass of the Earth, times radius of the Earth, right? This is how I know the field strength of the Earth. Now it's saying that Krypton has 4 times the radius and 2 times the mass. So 4 times the radius, G is the same. 4 times the radius, 2 times the mass. So it's 2 times the mass of Earth and 4 times the radius of the Earth squared. So this simplifies to G ME 2ME 2GME divided by 16 RE squared. Remember, I can divide gravitational field of Krypton by gravitational field of the Earth. So if I divide GK by GE, I'll end up with 2GME divided by 16 RE squared multiplied by RE, this one squared, we have to square it, RE squared divided by GME. So I can cross out things. The G is the first thing to go. The M equals the R squared also goes, and I just end up with 2 out of 16. So what I have is GK out of GE is equal to 2 out of 16. So if I want to know what is the best estimate for the magnitude of the gravitational field at the surface of Krypton, G Krypton is equal to 2 out of 16 GE, and it's just going to be 2 out of 16 times 9.8. So 2 out of 16 times 9.8. 9.8 times 2 divided by 16 gives you that answer, 1.225. That is G of Krypton, meters per second squared. That means this planet Krypton pulls things that are above its surface with an acceleration of 1.225 meters per second squared. Try this. I hope you can try this, and using the same idea that I've used here, you can try this out and see if you get that answer to be correct. Same as this, you can try it, or yeah. Let me try this one. G of Earth, remember G of Earth is where you start. GME out of RE squared. And the G of Tatooine, this planet Tatooine, is half the gravitational field strength and 4 times the mass of the Earth, right? So its GT of it's half, it's a quarter, sorry, it's half of GE, right? So I'll have half of GE equals G times mass of Tatooine, which is 4 times mass of the Earth, right? Divided by radius of Tatooine squared, right? So since it's a half of GE, I'm going to just substitute for GE here. It's a half of, instead of GE, I'll put GME out of RE squared equals GME out of RT squared. The GME and the GME cross out. So I'm left with 1 out of 2 RE squared is equal to 1 of RT squared. Simplify that, you have RT squared is equal to 2RE squared, and then if you take square root, then you have RT is equal to root 2 RE. So the radius of Tatooine, that planet Tatooine, is square root 2 times the radius of the Earth. I don't know if we'll have time today in class to go over this, so I was planning to talk about it tomorrow. But from here, you can start working on the rest of the homework questions which are posted on Google Classroom. I hope that helps. Have a good day.